Hello, chemists. Are we ready for a new topic? Let's jump into equilibrium. And so I'm going to go through the notes and then jump back and forth to the handouts every now and then. All right. So we are starting our journey on equilibrium. So in order to do that, we need to understand some basics of equilibrium. And the first basic is what in the world is equilibrium? And dynamic equilibrium, equilibrium. You don't have to use both terms. All right, it's two opposing processes occurring at the same rates. All right, this is an important part. Okay, it is occurring at the same rates, or if you will, the same speed, but that doesn't mean that it's equal concentrations of the reactants and the products. Okay, the forward and the reverse are at the same rate, but that doesn't mean they have to be equal on both of those sides. And then we'll see a whole bunch of examples and what that means mathematically. All right. One of the biggest difference between everything that we've done in the past and what we're going to be doing here is we have to now write things as an equilibrium equation. And an equilibrium equation has an equilibrium arrow, which implies that it can go both in the forward direction and in the reverse direction. Now, you're more than welcome to do something like that. So this one favors products, or that one favors reactants. But you don't have to make the two equilibrium arrows different as long as it's showing that it's going in both directions. So we've never done that before because we always did the one reaction arrow because that means it's pretty much 100% in one direction towards the products. And so we're going to be using a lot of acids and bases and things here in the future, and it's one of the easiest to show you. So this is vinegar. Okay, so this is acetic acid. And acetic acid, we know, will react with water, and it will make the hydronium ion and the conjugate base called acetate. But here's the beauty of that. As soon as the hydronium ion and the acetate start forming, they are just as likely to recombine into the acetic acid. And that's what is meant by the equilibrium. But you don't have to rewrite the equation over and over because the arrow is saying it can go in both the forward and the reverse direction. All right, so that's what equilibrium is. Now, equilibrium is dependent on many things, temperature being a huge one, but we need some kind of a mathematical equation. Okay, so qualitative is great, but we need to quantify it in some way, and that is called the equilibrium constant expression. This is not on your reference sheets because this equation is unique for every reaction that you do. So we are going to have to come up with a way to come up with that equation. And I have this next slide right here tells us about all the details. All right. So I'm going to go to the whiteboard and I'm going to put the details, but then I'll show you that slide. All right, let's go to the whiteboard. Oh, look, the whiteboard is still up from organic. All right, for equilibrium, I'm going to put that vinegar equation again. Now, one shortcut that we can do, never use a shortcut unless you understand why it works, but one shortcut we're going to start to do is we don't have to write out all of the molecular formula because really, if I'm talking about an acid, really it's the hydrogen that's important. So that's my nice little shortcut for acetic acid. And remember, when you do the ionization equation for acids, this and this imply the same thing. It's just a shortcut or it's shorter. This does not exist by itself, but it simplifies the equation. It simplifies it greatly. All right, what is an equilibrium expression? All right, it starts with an equilibrium constant. And that is a capital K. It's a big K. So rate constants are given the small k, but equilibrium constants are a capital K. Now that is going to be the products concentration raised to their coefficients. Oh, that's different than kinetics. Yes, it is. All right, divided by the reactants to their coefficients. So for this particular equation, the K is equal to, I'm going to do the long one, all right, I want you to notice I did not include the water. Equilibrium implies that you can go in the forward and the reverse direction, and any pure liquids are assumed to be so much in excess that they are not going to affect the overall equilibrium constant. So you are not going to include pure liquids, which will always have the phase label L. You're not going to include solids, because if there's a solid as part of your equilibrium equation, that means there's a whole chunk of solid. And then water, unless it's gaseous. All right, so in this case, we are not going to include the water. And all of the coefficients are 1. So of course you don't have to write the 1, but that implies that those are all 1. Now I'm going to go one step further, and I'm going to identify what kind of an equation this is. A, the subscript A, stands for an acid ionization. And there's a few that we are already familiar with. So the subscripts on your equilibrium constant. All right. Kc means that all the concentrations are in molarity. Kp means all of them are in, I don't want to say concentrations, all species are in pressure, usually atmospheres. Ka means this is an acid ionization question. Ionization. And this is the reason I hit it so hard in the last semester, is we were going to be using those reactions this time. So Kb means base dissociation. And right now you're thinking, wow, those words sound familiar, but I'm not quite sure exactly what it means. I'll do an equation for each one of them. Ksp is for a solid, oh, that's supposed to be an L, a solid dissolving solubility product is what that stands for. Okay, let me see. So Kc, Kp, Ka, Kb, Ksp, oh, Kf. Kf is generic for formation. If you'll notice, it's not as specific as the others, but you're forming a compound. And when we get to that point, I will show you some of those. And so a lot of times Kd is the reverse of that. So these two are often linked together. We think of dissociation, with the bases, but that just means you're forming it in one and you're breaking it down in the other direction. So those are very, very generic. All right. I'm going to do an example of each one of these now. So let's start with Kc. Kc means that everything is in molarity. So if I had, for instance, hydrogen gas plus nitrogen gas reacting together to make ammonia gas. Let me see, balanced chemical equation. Let's put a 2 there. Let's put a 3 there. All right, I have my balanced chemical equation. The K value, okay, now right now there's no subscript. I have to choose right now. I may either enter molarities or I may enter pressures. And these are all gases, so it could occur in both cases. Now I'm going to show you both of them. So I could put them in molarity, which is absolutely fine. And I could put the subscript C. But I could also put a subscript P, and then I like to do a capital P with a subscript just so it never, messes me up. So the pressure of ammonia over the pressure in hydrogen cubed, the pressure of nitrogen. Okay, and so that would be a Kp, which they are related. Okay, they are absolutely related. Because, oh, guess what? PV equals nRT. Oh, Pivnert. Remember, N over V is molarity, and so you can relate those two together because the only difference is time, not time, temperature. Okay? So that's the reason that we can go back and forth between Kcs and Kps, and that's the reason you can put pressures into equilibrium expressions. And I'm not going to solve those problems now, but Kc is equal to Kp, see if I can remember it, RT to the change in the moles of gas. We'll do that equation here in just a bit. All right, so there's an equation for plugging in both molarities and pressures. Let's do a Ka. Ka means it is an acid ionization. Which means you start with an acid, a weak acid, and I'm just going to use generic A for that. And if you'll notice, I'm leaving the phase labels off. Again, you should always put them, but it's not really the point of what we're doing. And so I do tend to leave them off, but it's never wrong to include them. All right, acid ionization means an acid reacts with water to make the hydronium ion and the conjugate base. And so that species is going to be the conjugate base. So this is just the shortcut version because I did not include the water, but acids don't spontaneously just throw their protons away. They have to react with the water in order for that to occur, which is why it's called ionization and not dissolution or just dissolving. Okay, because they're not just dissolving, they actually are reacting. So it started molecular, but it ended with ions. That is the power and the identity of an acid ionization. Those numbers we can look up in reference tables. And on the orange pages in your reference sheet, I give you a whole chunk of acid ionization equations. Now, Kb, on the other hand, just means it is a base, okay? All right, so we can either have an ionic solid dissolving, or a molecular base reacting with water. These right here, those belong in the KSP world if we're starting with solids, okay? So the moleculars are the ones that we're going to be really interested in. And ammonia is the one that we're interested in the most. Well, maybe not the most, but the key here, I have to have the water. And that's the difference. You'll always know the difference because this one doesn't need the water written because it's dissolving, but it's not reacting. Okay. For here, you have to have the water reacting. So that's the difference between a KSP equation and then using like an anion for a base. All right. Gonna draw my water just a little bit differently. The lone pairs on the ammonia, they're going to attack the hydrogen, and that hydrogen is going to give those electrons to the oxygen, and we're going to make NH4 plus hydroxide. And if you will notice, there's no way to leave the water out because it literally has to take part in the equation. And that would be called a Kb. So this Ka, equilibrium expression, would look like that. And the Kb one would look like, oh, don't put the water in. All right, notice right here. That is a gas, but I plugged it in as molarity. It will completely depend on what data you're giving, which one you're going to use. But if you see Kb, that means molarity. Okay, so if you want to look up the constants, you're going to have to use molarity. So if you're looking at your reference sheet, I'm talking about the orange sheets. And on one side, there's a whole bunch of Kas at 25 degrees. And then there's just a few Kfs that we're not going to use for a while. And then on the back side of that, there's a whole bunch of the next variation, which is KSP. And KSP is a solid dissolving in water. All right. So what kind of a solid? Well, an ionic solid. I should have said that. Ionic solid. Not reacting, just dissolving. All right. So for instance, if I put, oh, don't know why I can't think of one. Oh, let's just do sodium chloride. All right. Sodium chloride. Okay, I'm going to put some water above it. Now, the reason I'm putting it above the arrow is it's dissolving, not reacting. So I technically don't have to write it. And that is going to go to the sodium ion and the chloride ion. And if you'll notice, no part of the water occurs in the products. This is called a KSP equation. And notice, this is a solid, so it does not appear. And then, of course, the water doesn't appear, even though it's technically a reactant, it doesn't appear. So that is my KSP equation. Now, this one is interesting in that I only drew one arrow right here. All right, if you want to use an equilibrium expression, it has to be in equilibrium. And it has to be balanced. In other words, that equation isn't going to do you any good. So my question to you, is sodium chloride, does when it dissolves, is some of it going to turn around? Because remember, equilibrium means it'll go both directions, which implies the sodium and the chlorine will recombine to make the sodium chloride. And so, how do you know for these KSPs which ones to do? You're going to use the generic solubility rules for now, and we are eventually going to rely on the KSP values. And so the answer is if it is insoluble at all, you are going to use the equilibrium arrow. If it's pretty much 100% soluble, you do not use an equilibrium arrow. So sodium chloride is just one direction. So I'm going to change this so it's not. Let me see, who am I going to put sodium chloride with? So I'm going to change it to fluoride. Oh, but if you're looking at the solubility rules, all sodiums are 100% soluble. And so we have to choose or at least recognize our species. So I'm going to make it, whoops, come on, magnesium sulfide. All right, is there a question at all that that one needs to be in equilibrium? If we use the solubility rules, the answer is, oh, it's insoluble, and we can also find it on the KSP. So this one is valid. And right now you're probably thinking, wow, there's too many things to remember. I hope a lot of this is ingrained. The moment I started using sodium chloride, I hope you were thinking, well, isn't sodium chloride 100%? If you weren't, that's no big deal. It's the reason I pointed it out. There. Okay, that is the basic identity of a KSP equation. Now here is the difference between a KSP equation and a KB equation. So I can take sodium fluoride, okay? I can take sodium fluoride even if it's solid. And I can do a little equilibrium expression and I can just show it, dissolving. It's not really an equilibrium because it's 100%. Okay, that's one possibility. But I need to ask myself, will this react with water? And if the answer is yes, that's really not the equation I was interested in. Who cares about the sodium? Sodium is a spectator. Okay, we're going to go back to our net ionic equation. And what really is going on is the fluoride, after it's dissolved, will react with water. Now I'm in equilibrium to make HF plus hydroxide. That is what I meant by the difference between KB and KSP. And right now, if you don't recognize that, no big deal. But when I get to using KBs all the time, it'll start to be very obvious. All right, go back to our notes here. Make sure I covered all the subscripts. All right, so KC means they have to all be in molarity. KP means they all have to be in their pressures. KSP is for ionic solids dissolving. Ka, of course, is acid ionization. Kb is for base. And technically, is it ionization? Okay, so I'm just going to put base right there. And then Kf and Kd. Okay, form breakup. And that's what the subscripts. You do not have to have a subscript. Okay, you can have a generic K value. All right, the next equation is How do you come up with them? So everything that I said is right here. Step number 1, start with a balanced chemical equation. Step number 2, put all of the products in the numerator raised to their coefficients. Put the reactants in the denominator raised to their coefficients. And if it's heterogeneous, do not include pure liquids, do not include pure solids, and you may use the pressures for gases, and we prefer molarities for the others. All right, so notice this is completely generic. There is no subscript, and it would be C, because C is a product, raised to its coefficient, capital D raised to its coefficient, small d. Okay, A raised to small a, B raised to small b. All right, so zinc reacting with a proton. This happens to be an oxidation and reduction reaction. This is a solid. Oh, back up. You should start with a balanced chemical equation. Always make sure it's balanced. Yes, this one is. All right, the solid is not going to appear, but the other three will. So you write the big K, and everything can go in molarities. So right here, I put the hydrogen in, the zinc in, and then the proton squared. Or, do you see how I have a mix right here? Yes, you can mix pressures and molarities, but there's no subscript there. You're not going to be able to find those in reference tables. So the big K with nothing, those are harder to, I shouldn't say harder, but you don't have places that you can go get those numbers. But both of these are okay. You could put in either of those. All right. The last thing we're going to talk about is just where in the world did I come up with that equation? So Kc and Kp, when I was talking about those, I'm using the ideal gas equation. So there's your pressure, there's your molarity, and how are they related together? RT. And gases are dependent on how many there are. So N subscript G stands for the change in the moles of the gases. So for instance, if we were going to use that, I'm going to jump over to the whiteboard again. If we were going to use that hydrogen equation again, so hydrogen, there was 3 of them, plus nitrogen made 2 ammonias. All right, so for this one, if I gave you a Kc, these are all in gases, so I could also have a Kp. So I'm completely making this number up. I'm going to tell you Kp is 3.6. Okay, completely making that up. All right, I can either write this as Kp, the pressure of the ammonia, squared the pressure of the hydrogen, cubed pressure of the nitrogen, okay, equals 3.6. But what if I needed all of those in molarity? Well, guess what? Suddenly I don't remember it. Is it Kp or Kc first? I'm going to jump back over and peek. Yeah, this is one I don't use as often. Let me see. So Kp is equal to Kc. So Kp is equal to KcRT, change in the moles of gas. So the Kp is equal to the Kc. All right, R, these are gases, so we're going to use 0.0821 liter atmospheres per Kelvin mole. And in this case, do you notice I have to have a temperature? We are always going to assume that it is 25 degrees unless I give you another one. But I'm going to put that right here so that there's no doubt. At 25 degrees. And so that is 298.2 Kelvin, big brackets. Now the change in the mole of gases is the gases final minus the gases initial. And so I have 2 moles as the product, and I have 3 moles plus 1 mole. And so 2 minus 4 is a -2, and so that's what I raise this equation by. The only time they're going to be equal is when there's an overall no net. So if there's 2 moles on the left and 2 moles on the right, then the Kp will be equal to the Kc. So the Kp is the same as the Kc only when there is no change in the number of moles of gas. All right, that's how we're going to get between Kc and Kp. Mathematically, let's see, where can I write? It is just algebra, but let's solve this one. All right. So calculator. All right, so I'm going to take 0.0821. I'm going to multiply it by 298.2. And I'm going to do it twice to make sure I have the right number since there's nobody here to confirm for me. All right, so I have 3.6 is equal to Kc times sig figs. How many do I get? 1, 2, 3, 4. In the end, I'm only going to have those 2. So I'm just going to take 1 extra here. So 24.5. 24.5. And what unit is this? Right now, that is a liter, atmosphere, Kelvin, mole. And remember, that's what we're trying to get between is molarities and atmospheres. So I'm going to take that to the -2, which technically means this. And then I'm going to isolate Kc. So I'm going to multiply 3.6 times 24.5 squared. 3.6. And let me see, sig figs. Ooh, I get a whole 2 sig figs. So it's 2.2 times 10 to the third. Big in red. No units on equilibrium constants. Okay, there are no units on an equilibrium constant. One last example. How about hydrogen gas plus iodine gas going to 2HI? Again, I could do the equilibrium expression. I could do it in pressures or I could do it in concentrations. But Kp is equal to Kc times RT, the change in the moles of gas. But I wanted to point out there's 2 moles of product gas minus 2 moles of reactant. So that is a net change of 0. So Kp is really equal to Kc RT to the 0, that's a 0, and that is the big old number 1. So in this case, Kp is the same as Kc. All right, just a quick review of everything we've talked about in this little video. Number 1, what is equilibrium? 2 opposing forces at the same rate. or two opposing processes. Two, equilibrium equations. All right, how many equilibrium equations do you know? You now know acids, bases, KSPs, and we really haven't done any KFs or KDs yet. So acids, bases, and solids, not ionizing, solids dissolving into their parts. Make sure they're balanced. And the key is strong. They are not in equilibrium or 100%. Those are not in equilibrium. So that example I did of sodium chloride, well, the same would be for any of the 6 strong acids. All right, so if it's strong or 100% to the product side, 100% soluble, you wouldn't write an equilibrium equation. All right, after the equilibrium equation, you should always be able to write an equilibrium expression. Which is the big K is equal to the products to their coefficients over the reactants to their coefficients. And we know that K, which is the equilibrium constant, has no units. And it has no units. All right, last thing, the equilibrium expression. I guess I should put an A right here. The equilibrium expression can either be done in molarity, and if it's all done in molarity, it's called Kc. If it's all done in pressure, you may use Kp. Okay, those are just generic. You don't look those up in tables necessarily. Or you can do mixed or just generic. And you can just do K. And you can just do K. All right, and then don't forget Kp is equal to Kc times RT. If you want to get back and forth between them, that equation is on your reference sheet. And that is the generic basics or the beginning of equilibrium. All right, until next time, Jolly out.